Welcome to Dunwoody College of Technology, Mechanical Engineering Heat Transfer. This is MENG3250. We'll be working through an example from Bergman. This is problem 874. In this problem we're told that we have water at 290 Kelvin flowing at 0.2 kilograms per second through a Teflon tube, and we're given the thermal conductivity of that tube and the size of that tube. So the inside radius is 10 millimeters and the outside radius is 13 millimeters. And we're told that we have an electrical heating tape, wrapped around the outside surface and delivers 2,000 watts per meter squared. And outside that tape we have some ambient air that's giving us 25 watts per meter squared Kelvin on the outside at 300 K. That'll be our T infinity for that air. And we're looking to find what power is dissipated by the tape which goes into the water and what the outer surface temperature of that Teflon is. So to get started, we'll start with our known. Well, let's just talk for a second about our approach here. So looking at our approach, we'll draw a thermal circuit. Calculate some resistances. As part of that, we need HI to the water, and that will include some correlations or internal heat transfer. So we'll need some average Nusselt numbers for that. Maybe laminar, maybe something turbulent, maybe something in between. So we'll see where we end up. And once we have that, we'll calculate power to the water. And for last, we'll find TS for RO for the outside surface of that. Alright, so that's our approach. What are we looking for? Well, we'll start with our known. So what do we know about this guy? We have geometry of the tube, K for that tube, T for the water. We know HO, and we know T infinity for the air. Anything else that we know? I think we've got it. We know Q prime prime from the tape. So we know how much power we're putting into the system. What are we looking for? 1 power as percent into water, and 2, we're looking for the outer surface temperature. So it's a little schematic and a thermal circuit is helpful here. So our schematic, we've got some thickness here. I'll try to draw a segment of this guy. So our center line is going through here. Can't quite see the back side of this guy. There we are. And then we've got, on this, we've got some tape that's wrapped around. And outside of that, we've got another. That's our outer surface. TSO is what we're looking for there. We have HO. What did we say there? That was 25 watts per meter squared. Kelvin. T infinity out here is 300 Kelvin. We know in here Tm 290 Kelvin, and U is, or sorry, that's mass flow. M dot is 0.2 kilograms per second. We know that Ri is 10 millimeters. RO is 13 millimeters. So hopefully that makes sense. This is water inside of here. This is air outside here. Little thermal circuit here, and we're putting in Q double prime there. So our thermal circuit, we've got T infinity equals 300 Kelvin. Got some power in here. That was 2,000 watts per meter squared. So we're going to have R for conduction. It's going to be TS for the inside surface. And then we get RT convection in. This is RT convection on the outside. Right, so that's going to be 1 over HOAO, 1 over HI AI, and this guy in the middle here is just going to be that natural log of RO over RI over our area, which is 2 pi LK, where L is that thickness. And I think that gets us here, right? And this is TM for the water. TSO. We're calling this TSO here. Alright, so I think that covers it. That's what we've got going on for our thermal circuit. Some assumptions. Oh, and this is Teflon here. That might be helpful. K is 0.35 watts per meter Kelvin. Right? Yes. Alright, so there we go. And so assumptions. First assumption, we're going to assume we're steady state. Not told anything about time, so probably a good assumption. 2, we're going to assume that we have fully developed flow. We're not told anything about an entrance region or a length, so it's a good assumption there. In the absence of other information, we're going to have one-dimensional conduction, assuming that we don't have any significant variations along the length in terms of temperature in this Teflon section here. And we're going to assume negligible contact resistances. Now, from your conduction problem, project, you may realize that is possibly a bad assumption. In this case, when we're putting in that power there and it's adhered well to the surface, maybe not a bad assumption. That could be a place where we want to spend some time investigating after our initial analysis. Looking up some properties. What do we have here? So we have water at 290 Kelvin. What are we going to need for that water? We might need mu, depending on how far off we are from mu s. So mu, we're going to say that's 1080 times 10 to the negative 6th kilogram per second meter. K is 0.598 watts per meter Kelvin, and our Prandtl number for water is 7.56. Do we need anything else? Let's see, we have our properties for Teflon given to us. We know what the temperature of the air is. We know what the heat transfer coefficient for the air is, so we don't necessarily need any properties for that. I think that covers it. All right. So looking at this, what do we have going on? Well, let's take a look. So we know, let's go first, calculate our Reynolds number. So we have circular flow. What do we know? We have rho. Oh, I probably should have found rho up here. Excuse me. If we're at 290, we're about 1,000 for that. Or we can rearrange it. Right? We could rearrange this a little bit. Rho VD over mu. This can be 4 m dot over pi d mu. So just arranging a little bit here. So if we divide by the area and carry that through, we can get switches into mass flow. So if we sub that in, we get 4 times 0.2 over pi. Our inside diameter was 0.02 meters, and mu was 1080 times 10 to the negative 6. So carry that through, we get our Reynolds number. It's 11,789. What does that tell us? That tells us that that is well into the turbulent region. And we know we can use a lot of our correlations. A lot of our correlations had limits of Reynolds number greater than or equal to 10,000. So we're good with that. All right, so looking at that, let's find HI. We're going to need the internal Nusselt number. And then we're going to say that's equal to our fully developed Nusselt number, which using the Dittus-Boelter is 0.23, Reynolds number to the 0.8, Prandtl number to the n. In this case, are we heating or cooling our water? We're heating our water, so n equals 0.4. So filling that in, I have my Prandtl number up here. I just calculate my Reynolds number. 0.023, 11,789 to the 0.8. Prandtl number was 7.56 to the 0.4. All of that gets me 93.395 for my Nusselt number, which is also equal to HLC over KF. And in this case, what is LC? It's going to be my diameter. So I get 93.395 times K. Looking up here, we got 0.598 divided by 0.2 meters. Sorry, 0.02 meters. Sorry, inside diameter, right? We had 10 millimeters, so doubling that gets us 20 millimeters, 0.02, and so that is HI average is going to be 2,782.5 watts per meter squared Kelvin. So that's HI. Now we go back to our tape. So if we take an energy balance at the tape, we have the area there, 2 pi L times our diameter is RO. So 2 times the RO gets us our diameter times pi times L times our, that's what we have flowing in. Where that's going, we have TSO minus T infinity. This is the part that's leaving to the ambient air over 1 over HO 2 pi RO L. And then we have the part that's leaving into the water, which is going to be TSO minus Tm, that's our temperature difference, over, we get the two resistances, ln of Rho over Ri, over 2 pi Lk, we'll sub that value in a minute, plus 1 over 2 pi Ri L times Hi. Alright, so this is the part to the water. This is the part to the air. This is what we're putting in. So what goes in has to go out. These are the two paths for it to go out, either to the air or to the water. So rearranging that, we see we get a lot of pi's here. Our L's will cancel out. What else do we have going on here? In this case, RO will cancel out. Here we get an RI and RO carrying through. So as we rearrange this a little bit, we get HO times TSO minus T infinity plus TSO minus Tm over RO divided by K. It's a natural log of RO over Ri plus RO over Ri divided by Hi. Alright, so I got a little messy there, but not terrible. So we're going to fill in our values. So what do we get? We get 2,000 watts per meter squared. HO, let's see what we have back there. That was 25, is that right? Yep, we had 25 for HO. 25. We don't know TSO, so we're going to solve for that here first. TSO minus 300 plus TSO minus 290 over RO was 0.00013, excuse me, divided by 0.35, natural log of 1.3, 13 over 10, plus 1.3 divided by 2792.5. So the only thing we have unknown here is TSO. Solving that, we get TSO is 308.3 Kelvin. So we actually found the second part first. What does that tell us? Well, it tells us that we're confirmed that this is hotter than that air. So we get some heat flux to air. The air is not actually heating up our water, it's actually removing some heat from that system. What else does that tell us? Now we need to go back through. Well, we can either calculate how much heat flow goes this direction into our water directly, or we could do this one, which is slightly easier now that we know this value, and calculate this value, divide by our 2,000, and then subtract that away from 1, and that will tell us how much we get flowing into the water. Right, so we're going to do an energy balance. To air. So we get 25 times 308.3 minus 300. That bit is, so that works out to be 207.5 watts per meter squared. So energy to water, 2,000 minus 207.5. So that works out to be 17 92.5 watts per meter squared. It's a percentage. 1792.5 over 2000, set to be right around 90% flowing into the water. So we see that we're getting, if we insulated that, we could maybe get this closer to 1, right? But right now we're putting 90% of what we're putting into the system through electric energy into the water heating. Is that good? Well, the best we could hope for is 1, so it probably doesn't make sense to pay extra money to insulate this thing unless it's a super long line or something of that sort where we're trying to maintain this temperature over a longer period. So just to review our approach here, we drew our thermal circuit, try to identify our resistances. We use those resistances later. We found that the Nusselt number, find HI for those thermal resistances, calculated the power. Actually, we kind of did this one first. We found that outside temperature first, used that to calculate the power that went to the air and subtract that away from our power in, and we could find our power that we get going to the water. So we could find that as a percentage. So hopefully this was helpful. We used the Dittus-Boelter equation for this guy, right? We used that Nusselt number for an average Nusselt number. That's because we had the turbulent conditions. If we didn't have turbulence, we'd have to use the laminar. Again, that would be for constant heat flux 4.36 for our Nusselt. What do we have for our Nusselt down here? We had 93, so much better with that turbulence. So not surprising there. So I hope this was helpful for you. If you have any questions or comments, feel free to reach out to me and we can work through those before our homework is due. Thank you.